Hey guys, are there any questions before we get started on the lecture? We all good?
Yeah.
Okay, then let's get started. So today we're going to try to introduce the general E2 integral. So that's going to be denoted by an integral from 0 to t of delta u dbu, right? And this is a stochastic process. This here is a zero. This here is a stochastic process. Is indexed by t bigger than 0. So last time we considered delta u simple. So remember what that means. This means that if I take u in some interval, say tn to tn plus 1, so on that interval, I'll have that my stochastic process is exactly equal to the value it has at the left endpoint. So last time we considered these guys simple, which means that they're like piecewise constant. So you can find these TNs, right? So I can find these T's up to some Tn, such that on these intervals, delta is constant. Okay, so that does not include, for example, delta u being bu. So Brownian motion is not going to be constant. It's not going to be constant on a sequence of these intervals. So of course we want to be able to put b in here. So we need the more general E2 integral if we want to be able to integrate Brownian motion. Okay, so we need this extension. We need this generalization. We need to move from simple processes, the ones that have this piecewise constant structure, to these general integrals. So for us, we're going to have this delta u, right? This is a stochastic process, right? So it also depends upon omega. For us this year, this is a process such that delta u is if u measurable. I can see what is talked about when we talk about being adapted. And then the other property is that if I integrate from 0 to say t of delta u squared du, I'm finite. Right, so we'll just note. So just note that if indeed I consider delta to be just a Brownian motion, we have that bu is if u are measurable. And if I try to verify this condition here, I try to check it, what will I get? I'll have a bu squared here, du, and that's going to be equal to, the integral from 0 to t. I'll move the expectation inside. Bu squared du. And we have a Brownian motion. So I know what the mean and the variance are. Mean is 0, the variance is u. So I'll get here u. Du, this ends up being 1/2 t squared, right? And this is indeed finite. So the goal is to extend the definition we had last time to include all processes that satisfy this. In particular, that would allow us to integrate the Brownian motion. Are we good so far? So how to do this approximation? So the lemma that makes it all work, it says for such a delta, there exists a sequence. Let's call them delta un. There exists a sequence of simple processes such that when I'm looking at the expectation of, so it's this one over here I'm playing with. So over here I'm playing with such that delta u minus delta un, square it, integrate with respect to u, I compute the limit, let n go to infinity. This here is going to be 0. So this is the key lemma, and the proof here, this is really hard. The proof, this is hard. I don't know where you would have to go to find something like this. this would be in a PhD class. This is not so easy to get.
Professor, do you mind explaining what the expression means?
Which ones?
The one that you said the proof is ours for? Yeah, this one.
Dilemma?
Yeah.
Right, so you take one of these deltas, right? For such a delta, like the one we had before, you take a delta that satisfies that it's measurable and that this integrability condition is satisfied.
Okay.
You take such a delta that could, for example, be Brownian motion.
Okay.
Then it says, the lemma says you can find, give me any such delta, for example, that Brownian motion. Then you can find these delta n's that are now simple and such that this expectation here goes to 0.
That are not simple or are simple?
Yeah, they're simple, right?
Okay.
Because if they're not simple, it's easier. Just pick them to be equal to delta.
Okay.
Right? But I cannot choose delta n to be equal to delta because delta isn't not given to be simple.
Okay. Thank you.
Is the n an exponent or is just like some other way to index it?
I can index it like this. So maybe we could look at an example. If I take, so go back to this one.
Oh, so it's saying there's like countably many of them.
Yeah, there's a sequence, right?
Gotcha. Okay. Okay.
So what kind of if I were to take this, right, that's the one we've been talking about. How should I approximate that? So the lemma says that there is such a sequence of processes that are simple, but it doesn't say what it looks like. And there's no uniqueness statement here, right? It just says that there exists such a collection of stochastic processes. Could we try to create one here? How should we do it? Well, let's have a look. So I have a t somewhere. Maybe we should just pick one. Okay, so let's take t here to be 1 just for the sake of illustration. And so what I do is I need to have an index n to play with. So let me break this here into n time points. Actually, here I'll have 1 over, I'll have 1 over n. This is my first one, and I'll have 2 over n. I'll have 3 over n, all the way up to 1, which will just be n over n. Say I did that. So I'll have my time points, my tks would be what? It would be k times 1 over n. Right, so when I increase n here, I'm going to get more and more points in here. And I'm going to, like, if I go from n to n plus 1, or however we want to increase n, we're going to get more points in here. And so what should I choose for my delta u n? I need to define how this is going to look like on, say, an interval tk to tk plus 1. Any idea on how I should define my approximating sequence of simple processes for this particular one? So I start out here. This is where my Brownian motion starts, right? And then it will oscillate like crazy. This is how it will go. I need to say what should be my approximation on such an interval here from, say, 2 over n to 3 over n. What should I choose for my approximating sequence?
maybe like a slope, like a mean value theorem sort of thing.
Yeah, this is not differentiable, right? This
Oh,
is,
right. It's not. Yeah.
this might be.
It looks kind of smooth, but like there's actually like very like things going on.
This is what I mean when I'm saying that I can't draw it. Like, I cannot. It is impossible for me to draw a function without that function being differentiable somewhere. Like I can't do that. This is not possible, right? So if you've ever been taught in high school that a continuous function is a function you can draw without lifting the pen, let me just be the first to say that unfortunately your professor or your teacher in high school was wrong. This is not the definition of continuity. There are lots and lots of functions out there that are continuous and can never be made a picture. Weierstrass, he was the first one to come up with one around 1900. He was not popular back then because people believed exactly this kind of a thing that you should be able to draw stuff for it to exist. But that is just not how it goes. I mean, Weierstrass was right. There are functions out there that are continuous, and yet it's nowhere differentiable. And so you can just Google Weierstrass first function. It's Power motion is another one of these. You can draw it, but I'm trying my best here. How should we approximate? This is my delta, right? So we're looking here at u's between 0 and 1. I'm breaking up the interval 0 to 1 into smaller pieces, and I'm going to try to figure out how should I approximate. Like my delta on these intervals here has to be flat. So what value should I choose for my approximation on these pieces? Well, I could go up here and have a look there and keep it flat all the way out. And I could go up here and keep it flat here all the way up to say 4 over. So if I do that, I should pick on this interval, I should pick B, T, K. And if you insist on having the indices present, right, so it's my TKs that depend upon N. So I could put an N up here too. Just I'm overloading now on notation. And so would this work? Well, these are definitely simple, but do they satisfy this condition here? We'll try to work it out. What is this expectation there? So these are simple. These are simple processes. And let me do the calculation on the next slide. And if I look at the expectation of an interval, say from 0 to 1, delta u minus this delta u n squared du. Now what do I get here? Well, we'll plug in. So this is my delta. Delta, this was my Brownian motion. Now what about the other one? Well, the other one just was this thing here. This was this thing there. So this is more complicated to write out. So this is going to be something like is equal to BTK. And then maybe if I just want to write TK here, I need to break this interval up here. Instead, I should write this maybe as TK to TK plus 1, and then pull a big sum outside over case. Okay, so I could do this. And where will I be summing from? It will be from 0 and then up. What is the last one I can go up to? This would
minus
be
1 over n.
Yeah, it would be n minus 1. So does that go to 0 as n goes to infinity? And again, if you insist, we can put these n's on here. Well, let's have a look. See, if I pull the expectation operator inside, let me do that. So I'll pull the expectation operator inside. And then I'll take the expectation in here. This is BU minus BTK, and then there's N up there. What do we have here? What does that compute to? What does that equal to? Keep in mind here, U here is bigger than TK. Well, this is the second monad of a Brownian increment. And we know what that is. This here is equal to U minus TKN. So is that something we can integrate? We have to integrate this with respect to U. It's probably screaming that we should do a substitution. So maybe we should substitute here S being U minus TK. In that case, ds is du. Okay. I should also know that when u is equal to tk plus 1, and that's going to imply that s is equal to tk plus 1 minus tk. And when u is equal to the bottom one, that's tk, then s is going to be 0. Okay, so I can do that. I can then rewrite this integral here as a sum. And then I have my integral. Now that's going to become an integral from 0 to tk plus 1 minus tk. And then inside here, this is just going to be s ds. Now we're almost there. Integrate s. This is going to give me 1/2. One half times the upper limit squared. So what does that convert to?
Maybe we can pull out the 1/2 and then see if we can do something clever with the quadratic.
Yeah. We've seen stuff like this before, right?
Will a telescope? I mean,
Yeah. So how do we get a telescope thing? So we will write this here. So we pull the half outside. I want it to telescope, right? So I want to get rid of that square up here. So how did we get rid of the square before? We put out like a max. I think here it's even simpler, right? What is, yeah, I think here we made it, I'm making it too complicated now. What is this difference here, the way that we created it? I'm making it too complicated here. What is the difference?
1 over n. It's just 1 over n.
This is 1 over n, right? So
yeah.
So the 1/2 goes outside. I have a sum from k equals 0 to n minus 1 of 1 over n squared. Where does that go? Well, how many elements do I have? I have n elements. So this here becomes 1 over 2 times 1 over n. And this goes to 0 as n goes to plus infinity.
Wait a second. Was there like some identity that we have like 1 squared plus 2 squared plus 3 squared going on here?
Well, you're summing over k, right?
Oh, sorry. Yeah.
How many elements are there in the sum? There are n of them. But you're going to get n times 1 over n squared.
Okay. Yeah,
That's
much.
what I wanted.
Right. Yeah.
But you're summing here, this is a k, this is not an n. But you're summing up to n minus 1, there are n elements in the sum.
Right. They're constant. So yeah, I got
Yeah,
you.
I mean, this doesn't depend on k, right? So you see, it's a little bit tedious, but this one here, if I was just interested in Brownian motion, this sequence here of elementary processes, simple processes, this is going to do it. It'll satisfy the lemma, but only for that example, of course. No other questions on this? So given such a thing, given such a sequence, how should we define? Then we should define the integral of delta u dbu. How should we define it? Well, we know how we're doing the elementary ones. So this is going to be an integral from 0 to t of delta u n dbu. And we should somehow define this thing here as a limit as n goes to infinity. Because we know how to do all these ones. Because each one of these, this is simply just a sum over some case of, it'll be delta n of tk times the Brownian increment btk plus 1 minus btk. So what's the problem with writing stuff like this? Well, I bravely wrote a limit here, right?
Do you know it exists?
Yeah, so that's the problem. So how do we know? So in what sense, and I should say if any, does this limit exist? So this is not so easy, but I'm hoping I can give you guys a sense of it. So what I have over here is, if I take two, if I take n and m over here, and I look at this integral from 0 to t delta u n dbu minus this integral from 0 to t of delta u m dbu. And then a square, and I'll take the expectation. Okay. Okay, so pick n and m, and let's see what this difference here is. I can write this here as, I can use linearity. So I can write this here as an expectation of an integral from 0 to t And then we'll have delta un minus delta um dbu, and then there's a square. Okay, so I can use linearity of the integral. Then I have this square that's sitting out here. So now we need to remember what we did last time. There was something called the Ito isometry. Does anybody remember what the Ito isometry allows me to do?
The preservation of distance.
Yeah. So more specifically in this case here, how can I write this expectation here using Ito's isometry?
You pull the square out.
You can turn it into a Riemann integral. That's awesome, actually. This is exactly what happens. The square here travels inside.
Oh, inside.
And then the Brownian motion is replaced by its quadratic variation. Quadratic, it has to do with the 2, right? Quadratic variation. Quadratic variation Brownian motion, as Raksha points out, this is the Riemann integral. Okay, so where does that go? How big can this quantity get? Well, this is the thing I know something about, because the assumption is in the lemma, right, that these delta n's converge. You converge to delta, right? So if you want, what we can do is, if you haven't seen estimates like this before, but we could add and subtract in here. In here I could add. I could add delta u, right? That's the limiting object that we're trying to define the integral for, and then we could subtract it and add it back up inside this square here. And then I could use an inequality like the one if I look at how do I get this inequality? So if I look at a minus b squared, yeah, this is positive. I'm trying to derive an inequality that I'm going to use over here. So a minus b squared, this is positive, right? Because I'm squaring something. And this is equal to a squared, b squared, minus 2ab. And so I'll move the 2ab to the other side. I'll get the 2ab is less than a squared and b squared added up. Right, I'm doing nothing else. I'm just factoring out the square, moving the 2ab to the other side. We're going to get this inequality. And I can combine them and say, well, if I look at a plus b squared, well, I can do the same thing. This is going to be a squared, b squared, and instead of a minus here, and I'll have a plus 2ab. So this is going to be less than, if I replace 2ab by a squared and b squared. I am sure some of you have seen inequalities of this type before. So what that allows me to do now is to break this sum here. I can now write this. This is less than 2. And then the expectation of the integral from 0 to t, and then I'll have the first one will be delta un minus delta u squared du plus, and I get another 2 expectation integral from 0 to t, and I'll have my delta m minus delta u squared du. And I know that this term goes to 0, and I know that this term goes to 0, right? So this stuff here goes to 0 as m and n go to plus infinity, because that's the assumption That's the assumption I'm working on. I'm working under the assumption that my delta is such that I have the square integrability property and it has this measurability property. And I'm using the lemma to create these simple processes, and these simple processes have this property. Right, so that's what I'm writing down here at the bottom. So what does that show? So this is where it starts to get a little hairy, because we already talked about these LP spaces a few times. So what this here shows is that this shows that the sequence 0 to t of delta u in dbu, this is a so now here I'm indexing by n. This is a Cauchy sequence in this space L2. Remember last time we had this norm, we even have an inner product, we had this norm that would be the norm of a random variable x, the 2 norm would just be the expectation of x squared. So in this norm here, what will I have is that this integral from 0 to t of delta u n dbu minus this integral from 0 to t of delta u m in this 2 norm. This is the thing that goes to 0 as n and m go to plus infinity. So you might not have heard about Cauchy sequences before, but Cauchy sequences, they are quite important. In particular, one can ask questions like are all Cauchy sequences convergent? If you have not taken courses where you, like if you take a course in real analysis, this is something that might come up there. You might wonder, like, why is it, for example, why ever move? Why consider R and not just Q? Has anybody ever wondered about that?
Wait, consider R for what like for continuous time? That's
no, just when you were doing like calculus. Why are you working with R and not Q?
because Q is a countable set. So
yeah. What's wrong with countable sets?
Well, you wouldn't be if in the context of calculus, you wouldn't be doing an integral. You'd be doing like a discrete sum of if you're summing over like some set indexed by like the rationals, right? Is that what you mean, or
something? So have if I take a sequence, like I could take a sequence of numbers. If I take xn inside Q, and I could say if it's Cauchy, right, it just means that xn minus xm, this is going to become small. Right, so for any epsilon, I can find an n such that when n and m are bigger than n, this difference here is less than epsilon. So I could take a Cauchy sequence in Q, and then I could ask, is this convergent? So does xn converge to something in Q?
Not necessarily.
No. Now we replace it, and you say, what about if I take xn But now in R,
Oh, is the problem that Q doesn't include all its limit points?
yeah. Well, how do you describe limit points? You describe them as limit. There's no limit, right? You're just working here with Cauchy sequences. So it just means that you get smaller and smaller and smaller as you move out in tail. So if you have a Cauchy in R, well, then the answer is yes. Then xn actually converges to a point x, which is also in R. Whereas this point over here that you could get in the end, this x here in the end, this is may or may not be in Q. Right? So R is complete, Q is not. So it's quite important to have this completeness property if you want to describe convergence. And so the magical thing is that the space here, this L2 here, this has that property. Right, so the big result here, this is Fisher's completeness theorem. For LP spaces. And here we're just using it for P order 2. Fisher says that if you have a sequence that's Cauchy in an LP space, then there's a limit point. So now we're safe because I can now give meaning to what this limit here is. There is such an object. It comes out as a limit, not as a pointwise limit. This limit here is not pointwise. This is this L2 limit. It comes out as that limit. This is what is meant here. So I know this stuff here can be, this is a little hairy if you have not seen Cauchy sequences before. We have worked a little bit with LP spaces, but I wanted to give you like a little hint of maybe knowing something about LP spaces is not a bad idea. It's for martingales, it's very often L2 you end up working with. And the reason you end up with these martingales in L2 is because you always have quadratic variation. And quadratic variation is just a natural place where that wants to live, is in these L2 spaces. So let me go back to the example. So let's go back to the example. And let's work out what it is in this example. So back to the example where you have Brownian motion. Right. So now we know, and then we have our approximations. These were these delta U n. It was the left endpoint. When U was between tk n, tk plus 1 n. So now because the expectation of say the intervals of 0 to was it 1 we did? So maybe we should just stick to 1 here. Of bu minus this btk n squared, because this thing was going to 0, we now know that this interval from 0 to 1 of btk I'm missing a sum somewhere. I can't write it like that. I should write u down here of bu n. Let me write this again. This is too messed up. 6. So the example is delta u, what's my bu? I do the approximation, delta u n. This was b t k n when u is between t k n tk plus 1 n. That was my approximation from before, and we know that the expectation of the integral from 0 to say 1 of bu minus this delta u n squared du, we know that this converges to 0. This was from before. Let me just highlight where we did it. This was the calculation we had. This was the calculation we had here. It was this difference we integrate with respect to u. And we went through all the steps, and we ended up coming down here to 2 times 1 over n. Take the limit as n goes to infinity, you're going to get a 0 here. All right, so this was from page 3. So then, so then this implies, and this is from page this is from page 5. If I have that property, then these intervals from 0 to 1 of delta u n dbu now, I know that this thing here converges. It converges to a limit, which we call the stochastic integral of b with respect to Brownian motion. But what's the limit? Right, so we know that it converges, but we don't know what the limit is. This is again something that can be quite frustrating. Like, you can't draw Brownian motion, but you can work with it. And the same thing here, right? So we're getting these abstract existence results. We get that this thing here is going to converge ultimately because it's a Cauchy sequence in a space that guarantees that Cauchy sequences have limit points. But it doesn't say anything about what the limit point is, only that it exists. So in this particular case, what is it? So basically what we're doing now here is, maybe the first time you saw a Riemann integral, the first time you played with a Riemann integral, maybe what you did was you looked at the Riemann sums, and you proved that these Riemann sums converged. And then you manually approximated this function, computed the Riemann sums, computed the limits, and then this is how you got the Riemann integral of some function. This is basically what we're doing now here. We're just doing an example where we're trying to compute these things by working with the approximate sequence. And here we're just working with Brownian motion. So what kind of a guess, what could be a good guess? Guesses? What could this thing here, so let me put a 1 up here. What could this be? Like, maybe you'll use some intuition from calculus. If I am integrating from 0 to, if I'm integrating, say, x dx, what do I get here?
X squared.
Yeah.
Times 1/2. Yeah.
So this would be something with x squared.
Plus c. Oh, well, if it's not a definite integral.
Okay, so maybe I'll integrate here from, I don't know, a to b. And then I'll get x is equal to a, x is equal to b. Maybe I'll put a 0 up here. All right, good night, guys. You have to have good night, guys. Good night, guys. So maybe I'll put a 0 down here, and then we'll just get that this is 1/2 b squared. So what would be a guess here?
1/2 bu squared.
Yeah, so now we integrate up to 1, right? So this would be b1 squared. Does that seem like a reasonable guess? But be careful, right? Because what was it we saw last time?
Correction term.
There's a correction term. Can we almost like sense why there would be a correction term here? This is, when I looked at the stochastic integral, like these ones up here, like last time we proved some properties of this thing. What was one of the main properties we had?
Was it a martingale?
Yes. Right, we had this thing, this is a martingale. So if it's a martingale, it has expectation equal to
0.
What about this guy? If your guess is right, Richard, which is a good guess, what is the expectation of this thing?
Does it also have to come out to? I'm not sure about this one.
Well, let's just compute the expectation here. The expectation of 1/2 b1 squared, what is that equal to?
B1
Times 1/2, right?
Yeah, times yeah.
That doesn't look like a martingale, does it?
So we just subtract 1/2 from this.
Oh, so now you're changing your guess.
Yeah.
So what is your new guess now?
1/2 b1 squared minus 1/2.
Aha, so there's a correction term. Fantastic. Is it true? Right, we're just guessing. But I'm hoping you can see how if you just use what you have learned in calculus, you're going to be led to this 1/2 b1 squared. That doesn't mesh very well with the martingale property, because the martingale property would dictate that this expectation here had to be 0. So there's a correction term. This is a sub-martingale because of a convex function of a Brownian motion. It's going to give you a sub-martingale. So it's something that increases. You've got to bring it down a little bit. And so the guess is, the offer on the table is to subtract away minus 1/2. Okay, so can we prove this? Let's try to give a proof. Let's try to give a proof, right? So let us compute. Let's compute the limit. So this was the limit in this L2 sense of the integral from 0 to, I keep writing it T out here, 0 to 1 of delta U n dvu, right? So this was the limit as n goes to infinity. This was the sum from k equals 0 to n minus 1 btk n times btk plus 1 minus btk. So what is this equal to? We know it exists. Richard came up with a guess. Either we're going to dispute Richard's guess or we're going to verify it. It's always a very good idea to have a guess before you start doing calculations, right? Because you can always go back and change the guess. But it's a good idea to have something to start out aiming for. how would one go about doing this? Well, if I look at, let's try something like b tk plus 1 squared minus btk squared. So I can make a decomposition here. I can write this here as, what would it be? It would be btk plus 1 n minus btk n, and put it inside a square. And then I need to do corrections. I need to do some corrections here for this to work. Need to do 2 times, what would it be? btk n times btk plus 1 n minus btk n. I think that's how it goes. Let's just do a sanity check. I get this one squared, that's good, that's what I need, and I get plus this one squared, that's way off. Then I get minus 2 times it here, so that's good, it clears out. Then I get 2 times the cross term, and I have that here with a plus sign, and here it comes with a minus sign, so we're good. And so if I sum the left-hand side, I'm going to get the same thing as when I sum the right-hand side. And if I sum the left-hand side, this is now a telescoping sum. I'm just going to be left with the last and the first. This here is equal to b1 squared minus b0 squared. And of course, if I sum the left-hand side, I can do the same thing if I sum the right-hand side. So here I'll be summing btk plus 1 minus btk squared. And then 2 times, and then it'll be the sum btk times that increment btk plus 1 minus btk. Okay, so the left-hand side, there's no dependence upon n, it's a telescoping sum. Now the right-hand side, where does the first term go?
Goes to 0.
No. Doesn't go to 0.
Is the difference still 1 over, is not 1 over n anymore, or?
It is.
Oh, it is, okay.
Where does this thing converge to? What do I get when I add up the differences squared and take the limit?
Wait, hold on. The difference is still 1 over n, right?
Yeah, between the tk plus 1 and the tk.
Yeah, and then we square that.
No, we take the boundary motion at tk
Mhm.
plus 1 minus the boundary motion at tk.
Is it 1 over n?
No. What did we work on last time, guys? What would happen here if I just put absolute values instead of a square?
I think we need a hint.
So what was it we had last time? We took f from 0 to infinity to r. I looked at the sum of f at points tk plus 1 minus f at tk, took the absolute value, and I took the limit as this mesh would go to 0. So in this case, it's just my ends. I would get something, and then I could also look at the same thing. But I'll take the limit as n goes to infinity of the sum over k's, and then I'll take the square. What would this thing convert to? What would this thing convert to?
Wait, does this have to do with the first variation, second variation stuff or not?
Yes, that's what it is, right? This here was the first variation of f. This one here was the quadratic variation of it.
So I think I remember quadratic being finite.
Yeah, and what's the quadratic variation of Brownian motion?
Be TK, right? Uh,
No k, right? Or just k is just a dummy we're summing over.
wait. All right, I'm lost.
No, you're on the right track. But we had our interval. We're looking at the interval from 0 to 1, and then inside here you have your tk plus 1.
Right.
Timon, you're right, just 1. This was the term you wouldn't get had you done calculus. Because if this would have been a smooth function, the quadratic variation would have been 0. And then the last term, well, the last term, this is exactly our integral, right? This is 2 times that integral of bu dbu.
Oh wait, so the calculus thing is really just a special case of this thing, because it turns out to 0 when you have a smooth function, differentiable function.
Yep.
Why is this one again? I'm sorry, I don't think I understand.
The quadratic variation of Brownian motion, we did that last time. The quadratic variation of Brownian motion of the time t is equal to t.
Oh, and we're at time 1, so that's why.
And that's how we did it, right? We were interested in computing up to time.
Okay. Yes. Got it.
So there's the result, but that was being conjectured, right? 2 times the integral of bu dbu is equal to b1 squared minus 1.
Oh, and we know b0 is 0, so that just goes away.
So that's how this is. So of course, more generally, if I will look at the integral from 0 to t of bu dbu, we will be able to do the same thing. There's nothing special here about the t being 1 here. We just get a t here, we get a t here, we get a t here. This would be b, maybe I want to put a 2 in front here, bt squared minus t. And this here is the martingale, right? So that's our first stochastic integral. One thing I'm trying to get across here is that please don't treat that there are some mistakes that you should not make. And please don't treat the stochastic integral as your regular good old Riemann integral. If it was that easy, we would not have these lectures. Right? And as Richard says, it is true that what we're doing is has as a special case this Riemann integral. That's true, but it will always be, when you're dealing with Brownian motion, you always have this extra term coming up. So that special case is not that is not something that we typically end up using. We always have this extra term. And as you can see from this, it's pretty tedious. It's so the shortcut to calculations like this is the chain rule. Just like in calculus, you would not compute this integral here. While you could, you would not compute upper and lower sums approximating this integral here, Riemann sums, and then do it, right? What you would do is you would find a function that has this thing here as its derivative, right? So that's the chain rule of the fundamental theorem of calculus. So this is called Lieto's lemma. Some people call it Ito's formula. And there are a few people that call it Ito's rule. It has somehow never ever been called. It's not called the theorem. It is kind of funny. It never reached that status. It is by far the most used theorem in stochastic analysis. Stochastic calculus is what we're doing. It never got the status of a theorem. It never got the status of a proposition. It remained a lemma. And let me just show you how that works. So here's what you do. You take a function, take a C2 function. So you're going to have two derivatives, and you're continuous. So f goes from, it's just a function that goes from R to R. Nothing fancy. This is one of your favorite functions, so examples. F of x is like square. F of x could be, the other one we'll do in a minute, is e to the x. Take a function, has two derivatives, that's it. Nothing random about this.
You mean like it's twice differentiable?
Yep.
Okay.
So there are two derivatives, they're continuous. So then what? Then Ito's rule, Ito's lemma. I need more paper here. So Ito's lemma says, if I want a new stochastic process, I can get one by composing this non-random object called f here. I can plug in Brownian motion here. And if I were to just follow the standard calculus, I'll be able to write this as f of b0, say, plus an integral from 0 to t. And then I'll have f prime of b dvu. That will be the standard version. Ito's lemma says not so quick. You're going to need one more term here. And that's why we need two derivatives. You need f double prime here. And then you need the credit gradation of Brownian motion. That's Ito's rule. And so if we go back to our example, f being a square function, and f prime is of course 2x, f double prime is 2. If anybody wonders, this looks a lot like Taylor's formula, right? This half here, this could have something to do with Taylor. This is like a second order Taylor, whereas you used to the first order. Anyway, that's where the half comes from, Taylor's formula. So what do we get? We get that bt squared is equal to f, so that'll be b0 squared, plus an integral from 0 to t, f prime was 2bu dbu, plus, and then here you have 1/2, and then it will be 2 du. And so if you work it out, that was a 0. You will get 2, the integral from 0 to t, bu dbu. Over here we'll have 2 and 2. This is canceling out. I just get t. So that's just a lot faster than going through all these approximations that we just did.
So is it true that we only need to go up to the second term? Well, I guess it's the third term for like this Taylor approximation, because the second variation is finite, so it converges like
Yeah, so what do you think the third variation is?
0.
Yes,
Oh, so that's why you don't need to consider more terms.
that's right. So you might sit there and wonder now, could I throw something at you that would have like 7th variation, and we would need Ito's lemma with 6 terms, or however many terms we need in there. So for martingales, it stops at 2. Because their correct variation for martingales, this is finite. So stochastic analysis, stochastic calculus, we will not need more terms. I have not seen a branch of math where you go up to higher terms, 3 or 4. I have not seen that. I would not be one bit surprised. I mean, so I know there are functions out there, lots of them, that have this property. The extensions that I have seen that go beyond like this kind of stochastic integral, where something like Ito's formula breaks down, has not been about putting in more crazy stuff in there. There are definitely ways to make Ito's formula break apart. Yeah, I have not seen one where you have like multiple terms up here. At least not on top of my head. Let's do one more example before we call it a night. So another example that we have had fun with is the exponential. If I take f of x to be e to the x, then of course f prime of x is the same thing as f double prime of x. This is the same thing as e to the x, right? And so then Ito would produce that the exponential of bt is equal to the exponential of b0 plus an integral from 0 to t of what we get here, we get f prime, so that's the same. This is e of bu dbu plus 1/2 integral from 0 to t e bu dbu. And so this one here, this is equal to 1. You also, yeah, now you're going to get your first, this is an example of your, maybe your first, this is our first. It's called an SDE. It stands for a stochastic differential equation. And it's called an SDE. And it's really confusing that it's called a stochastic differential equation, because the appropriate word, recognized by everybody but used by absolutely nobody, is to say the word integral here. Nobody says that. It's always called an SDE, even though it has an integral in it. If I were to write down like as ZT, I wanted CT to be equal to 1 plus an integral from 0 to t, and then here I would write CU dBU plus 1/2 integral from 0 to t of CU. This should not be B, right? This should be a U here. TU. Right, the last one is the TU. The last one is the TU. So you can see here, if I didn't have the first one, if I didn't have this first Brownian integral, right? So I'm giving you, find a function such that that function is equal to 1 plus 1/2 times the integral of that function. You would be able to figure out what this is. Like if I were to give you, I'm really just out of paper here. So compare with calculus. If I were to give you a ZT is equal to 1 plus, and then this 1/2 integral from 0 to t of CU du. Like what kind of a Z is that? Well, you would then note that Z0, that's 1. And you will note if I take the derivative, CT prime, this is going to be equal to 1/2, it's going to be equal to 1/2 CT. So what kind of a function has the property that it starts at 1? When you compute the derivative, you're going to get 1/2 of the function.
Maybe logarithm?
The logarithm, if you take the derivative of the logarithm, you get what?
1 over x.
Yeah, that won't work, right? You need something
Yeah.
like this. So it's equal to what here? It's not the log, it's the right, e to the 1/2 t. So if I gave you this equation, you would know that I'm talking about this function.
Oh, it's a differential equation with like
It is,
an
right?
initial condition. Yeah.
So now we're doing something that's more complicated, right? I'm not just giving you the last term and the first term, I'm also giving you the middle term. Right? So it becomes a stochastic differential equation. So it has your usual term, and then it has this middle term here, which has Brownian motion. So find a stochastic process that's satisfied all this stuff. Can you do that? Well, the answer is yes. The answer is that this one here is the same thing as saying that CT is equal to e to the BT. Okay, I think this might be the place for us to stop tonight. Are there any questions in the last few minutes?
So the whole idea here is like calculus, but for functions, because you're using random variables.
It's,
like
that's why it's called stochastic calculus.
Okay, that makes sense.
Right? It's
Yeah.
calculus, you're going to change all your rules that you know from calculus. So let's have a look at how they work when you have a stochastic process like a Brownian motion in the middle of it. Right. So I'm just hoping that I can get it drilled into you guys that whatever you do when you're facing such a situation, right? And we're going to be facing this situation here for the remaining part of the course. Every time, let me tell you a personal story because sometimes that sticks better. My wife, right? We are in the same field. When she was a first year PhD student, she knew this stuff here, and she had to take an exam. She took an exam, and she was like, "This is kind of funny how they didn't ask about Ito's lemma." And I was like, "What are you talking about?" I guarantee you they talked about Ito's lemma in this exam somewhere. And she's like, "Shoot, I forgot the term." And so she remember now, here 15 years later, she took this one exam, and she forgot that term. And this will still bother her. So I'm trying to get across now here in the last 5-6 weeks when we work with stochastic calculus. Can we please all make a serious effort in never ever forgetting this term here? This is there. This is what makes a stochastic analysis. Without this term, it's just calculus. With this term, this is the stochastic calculus. This is a new thing. So if you find yourself in an oral exam with me in a few weeks, and you're missing this term there, please correct it before we're done with the exam. So you don't have to be haunted by this like my wife still is. As he moved on at some point, but yeah. Okay. So that's important. This is what sets calculus and stochastic calculus apart.
Wait, so Professor, so when we're doing all the prior work we did, right?
Yes.
Does it all boil down to what we just came to right now?
I mean, for the continuous analysis, for the continuous time stochastic analysis, this here is the key formula. This is how we'll get Black-Scholes. This is how we'll get the replicating portfolio. This is everything oozes from this formula here.
Okay.
I start pricing things with this formula now. I just have the
Well,
data.
you can use this for everything, right? Stochastic analysis was not developed in any possible way for math finance. It's just math finance is an application of stochastic analysis, stochastic calculus. And this term is sitting right here. This is the quadratic variation of Brownian motion. So if you're willing to accept that, you can very quickly move beyond just looking at a Brownian motion here. Then the formula should be that whatever you put here, you're going to put d of that thing here, and you're going to put d of the quadratic variation over here. Right, so if I were to move beyond this, the general formula is going to be something like a yt is going to be f of y0 plus an integral from 0 to t f prime of y dy plus 1/2 0 to t f double prime of yu, and then d, and then you need the quadratic variation of y, sorry. This is going to be the general, this is going to be the most general formula. Well, this is going to be the most general formula that we have when y has continuous paths. If there are jumps, then you have to change this. But we're not going to go there. There was another question in the log. Let me just look it up. Rohan, I'll try my best. I like it, Rohan. We're going to do some practice problems. Don't worry. We will be practicing on this here for a few weeks, itching closer and closer towards math finance. Tian is asking, soon, will you post notes soon? I can try to go down and see if I can get the scanner to work. And then I'll post them later today. Alrighty. So again, there are office hours tomorrow morning. And if there are no other questions, I have a good night, guys. And I hope to see you either tomorrow morning or next week.
Thank you, Professor.
You're welcome.